Hello, my name is Rupali and it is a pleasure to present this work carried under the guidance of Dr. Mainak Alikari. This work is titled as Real-Time Prediction Using Fog-Based Federated Learning and Genetic Hyperparameter Optimization, which is published in IEEE Transactions on Network Science and Engineering. We are thankful to the journal for the thorough review and generous acceptance of our work. In this work, we propose a novel FL framework that leverages fog nodes and genetic algorithm to address challenges such as single point failure of the central server, communication overhead, client-side efficiency, and client-side hyperparameter optimization. The proposed framework leverages fog nodes in FL framework by using fog nodes as intermediate aggregators between the clients and the central server, which reduces communication overhead and increases the robustness of the FL framework. Further, we use the genetic algorithm at the fog level to optimize the hyperparameters for each client, making use of the inherent exploration and exploitation in genetic algorithm to find the optimal hyperparameters. The figure here shows a high-level diagram of the system model. The proposed framework consists of edge devices located in different geographical locations that use their local datasets for model training. Fog nodes placed in the geographically close proximity to the edge devices aggregate the model updates from the edge devices. A central cloud server CS connects all the fog nodes. The framework operates in three tiers. Tier 1 or user layer. The user layer in Tier 1 consists of sensors which act as raw data sources connected to the edge devices. The edge devices are resource-constrained IoT devices used for integrating the rich information and knowledge from the IoT layer with the AI. The Tier 2 or the fog layer. This layer contains fog nodes embedded between the edge devices and the cloud server. They exhibit a behavior similar to the cloud server but with low computation compared to the cloud server. This way, the edge devices need not reach out to the extreme end cloud servers, reducing the communication latency and bandwidth consumption. The fog nodes play two roles, local fog node and global fog node. A local fog node is a fog node that is responsible for aggregating the model updates from a subset of edge devices, while a global fog node is a fog node that is selected to aggregate the model updates from all the local fog nodes. The Tier 3 or cloud layer. The cloud server coordinates the global fog node selection process. However, our system is designed to cope up with the worst case scenario of failure or attack on the cloud server. In such a situation, the fog nodes will communicate with each other and elect a new global aggregator among themselves based on the resources and the network availability. Moreover, if a global fog node fails, the cloud server will take over the responsibility of global aggregation to ensure optimum resiliency. The figure illustrates a detailed view of genetically optimized fog-aided federated learning methodology that combines fog computing and genetic algorithm in the classical federated learning framework to enhance its real-time performance. Hyperparameter optimization or tuning plays a vital role in FL framework due to the presence of high heterogeneity. Also, to tailor the client-centric performance optimization, the globally learned FL model needs to be tuned with client-specific hyperparameters. In our scenario, we use the genetic algorithm for customized client-specific hyperparameter tuning of the model deployed on the edge devices, that is the clients. This figure illustrates the process of hyperparameter optimization at the local fog nodes using genetic algorithm. Genetic algorithm is employed at the local fog level rather than the edge because edge devices are resource constrained and hence offloading this computational task to the fog layer would be more efficient. The basic steps involved in the optimization problem using genetic algorithm are selection, evolution, crossover, and mutation. The selection process happens when the edge devices share the best set of hyperparameters with their corresponding fog nodes for each round of local aggregation. Each edge device clones the model for all sets of hyperparameter and trains each pair of model for a certain number of epochs on its local dataset. We use a select we use a selective model cloning strategy that only clones the model parameters that are affected by the hyperparameters, which can reduce the amount of data that needs to be copied and transferred between the edge devices and the fog nodes. For example, if the learning rate is changed, we only clone the gradient values of the model parameters, not the actual parameter values. After the training is completed, it evaluates the best value of the hyperparameter or learning rate based on the loss. The value of the hyperparameter with minimum loss value is and the recent model parameter updates are shared with the local fog nodes for local model aggregation. At the end of every local iteration, each local fog node receives a set of best performing hyperparameters and updated model parameters from all the edge devices in its vicinity. This forms a new population in terms of genetic algorithm, consisting of the client or of the best or the elite performing values of hyperparameters from all the edge devices. Each local fog node then sorts this population of the pair of hyperparameters and on the basis of loss in ascending order of loss. In crossover process, a pair of learning rates is chosen as parents to generate a new learning rate referred to as offspring. Terminating the genetic generation of the optimized hyperparameters value at the end of the crossover phase leads to the process of to be stuck in the local minima. So a strategic trick is to mutate the newly generated offspring by a small factor, thereby introducing exploration in this process. Since at the edge devices we clone the model updates for each set of optimized hyperparameters and train each of these pairs separately, thereafter, we select the best performing pair of hyperparameters and model parameters by sorting them in ascending order of the losses and choosing the pair with the least loss. This process of elimination of worst performing model parameter wards off the forged model parameters. Figure shows the experimental test bed setup, which consists of the global fog node, the local fog nodes, edge devices, and the sensors deployed for data collection. We now move on to the parameter settings. Since optimizing all the hyperparameters can be computationally expensive for an experimental purpose, we only optimize two hyperparameters, that is the learning rate and batch size. The other hyperparameters are experimentally set by doing a thorough performance analysis. For example, for setting the optimizer, we compare the performance of 5 popular optimizers on model accuracy by fixing the other hyperparameters to the best values. Similarly, to select the activation function, we apply the same process and evaluate to find the best performing activation function. We evaluate the performance of our proposed framework based on the accuracy it achieves. We consider different scenarios such as accuracies attained in 10 global iterations or aggregation rounds, 15 global aggregation or iterations, and 20 global iteration rounds. We also perform a comparative analysis with the state-of-the-art FL approaches. The state-of-the-art federated versions, namely Fed average, Fed adagrad, FedAdam, and FedYogi have been implemented on our dataset for comparison of their accuracies and loss. Also, these versions have been embedded in the proposed GA-FOG-FL framework to have an optimal analysis of the performance of all the techniques on the datasets. Results demonstrate that the proposed framework seamlessly integrates the different FL versions to, to obtain a comparatively better performance. Further, here are the results of our testbed setup that evidently showcases how proposed methodology outperforms classical federated learning and conventional ML performance in terms of accuracies and losses attained in 20 iterations. Thank you.